welcome back. Video number 2, chapter 9, starting on question 9.29. Here we go. 9.29. The equilibrium constant Kc for the reaction of H2 and I2 is 54 at 425 degrees Celsius. If the equilibrium mixture contains 0.015 moles of I2 and 0.03 moles of Hi, what is the concentration of H2? Let's write out the reaction that it gives us first. We have H2 plus I2 yields reverse reaction 2Hi. Awesome. No big deal. No big deal, easy stuff. Alright, so, see that 425 degrees Celsius? Doesn't matter. Go ahead and delete that from the question. It literally does not relate to anything. So, let's continue on. It asks us for what is the concentration of H2. So, we have to use our Kc formula for this. Kc, as we all know, products over reactants. That is the formula for Kc. So let's plug in what we have. It says that the Kc is 54, so 54 equals, it tells us this is 0.03, and it's squared because that big 2 right there, that makes it squared. If that was a 3, it'd be cubed, etc. It tells us that, let's see here, it tells us that I2 is 0.015. We're just plugging in for the Kc here. And then we don't know what this is, what the H2 is, so it's going to, H2. So it'll just be X. Let's call H2 X. So, you know, back in like 10th grade high school, you had to solve for X and it sucked. This is just like that. Here we go. We're going to start off with rearranging the formula. Hope you have that written down. If you don't, just fast forward, rewind the video, pause, write it down. If you need to write it down. Hopefully you can just jog it in your memory. Alright, so let's get X by itself. To do this, we have to multiply both sides by X. So times X times X. Putting an X here, as you all know, will make the X's cancel. That's how algebra works. It's just the rules. I don't make them, I just follow them. So that means we have 54X equals 0.03 squared over 0.015. Easy stuff. This looks really, really complicated, and I know it kind of is, but it's easy. Again, pause the video, write that down if you need to, because it is gone. Alright, so, let's do the math. First, we're going to start off, you don't want to have to divide all this by 54. That gets into more complicated rules that we can just avoid. Let's start off by getting this into an actual number. So, 0.03 squared is 9 times 10 to the negative 4th. Screw that. Don't even hit any more numbers. Let's just divide that by 0.015. To get a workable number, hopefully. Yes, 0.06. So 54x, 0.06. This is easy. Now, you don't get x by itself, right? You just divide by 54. So x equals 0.06 divided by 54. I hate this freaking tear right there. I bought this board today for like 10 bucks at Home Depot, duct taped it to my wall to get the job done. But this is a big board. It didn't fit in my car. I had to bend it this way to get in my car. And it broke. The things I do for you people. The things I do. So let's divide and get the concentration. 0.06 divided by 54 equals 0.001111. So this equals 0.00111111. Another way to write that, the proper scientific way of writing it would be 1.1 times 10 to the negative third, because decimal moves 1, 2, 3 places to hit a whole number, so it's the negative third. And that is the concentration of H2. Simple stuff. If you didn't get it, just rewind, watch it again, it'll click, I promise. You're all smart people, we're all smart, we all can do this. It's no big deal. We're going to get that curve, we're going to get freaking hundreds and everything from here on out. Moving on. No, doesn't matter. Here we go. 9.34. So, this is on page 362 if you're following me. Hopefully you are. I mean, you kind of have to follow me to watch these videos or else it just won't really work. Ammonia is produced by reacting nitrogen gas and hydrogen gas. For each of the following changes, indicate whether the system shifts in the direction of the products, reactants, or does not change. All right, this is easy. So let's start off by writing our formula. And it's N2 plus 3H2 yields reversible reaction, 2NH3. Let's draw our products down here. Plus 92 kilojoules. These kilojoules, that's heat, temperature. That's what that is. So don't let that confuse you. It's a very simple thing. All it is heat. No big deal. All right, so now we're going to see what these different things do to change this and what change actually happens. So part A says, remove some N2. All right, so if we remove some N2, remember how I said earlier about, like, in the last video actually, about how things hit each other and that's the reaction happening? So if you take some of these N2s away, the 3H2 will have less molecules to react with, therefore it'll slow down. So to speed things back up again, this side is going to start feeding or start happening more quickly. So it's going to shift in the direction of the reactants. And next up is lower the temperature. So if we lower the temperature, let's say to 82 degrees, or sorry, 82 kilojoules. Kilojoules are not in degrees. All right, so you have changed it to be 82 kilojoules. This is now no longer at equilibrium. This, equilibrium, no big deal. But if it was 82, no longer at equilibrium. So the reaction is going to have to get it back to normal by adding more heat. So to add more heat, it'll react more on this side quicker. So it's going to shift in favor of the products. So if you take heat away from this side, it'll change to the products. If you added heat, it'll have to cool it down by reacting more on this side to remove some heat, and it'll go that way. I'll get into that right after I finish this problem. Because temperature is kind of the opposite of what you'd expect. So add more NH3. Adding more NH3 would cause it, it's just like this. Adding it would cause it to shift in favor of the reactants because if you added more, it has to get rid of some of that to get it back down to normal. So it'll react quicker over here and bring it in this direction. So it'll shift in favor of the reactants, aka to the left. Alright, let me go over that temperature thing really quickly. And then I'll do one more problem, that'll be this video. And then after that, it'll be the challenge problems. Alright, so, in the book it says, let's give us an example here. We have, and there's two types of reactions in terms of temperature, endothermic and exothermic. Let me write an endothermic for you. Products are down here. Alright, the book says that if you increase the temperature, it'll shift in the direction of the products. It'll shift this way. Because it has to shed off some of that extra temperature to get back down to equilibrium. So it's going to react quicker on this side, which moves it this way. Boom. Easy. So if you were to cool it down, let's do that. If you were to cool it down and put it down to, let's say, 4 kilojoules, it has to get back up to 5. So instead of shifting this way, it'll shift this way because this part is now reacting quicker to get more stuff over here, which will help increase the temperature. So that's basically the rules of that. No big deal. Pretty simple stuff. If you don't understand that completely, go to your book. It's on page 360 and 361. Just read what it says. That'll explain it perfectly. And probably much better than I can, because I don't write science books. I'm an English major. I mean, come on. I could probably write books, but not science books. Okay, 9.3. We just did that. Actually, that's the video, isn't it? That's the end of the video. Next up, I'm going to jump into the challenge problems. So get ready for that. That'll all be on page 366. Thank you for watching.